So my seminar portion of this culminating project was based on the Big Bang Theory, which is the origin of the universe. So the Big Bang Theory initially began from the observation of Edwin Hubble, and he noticed that other galaxies were moving away from our own galaxy, so they were redshifting at great speeds in all directions, and it had been as if there was some ancient force to have caused it, which we still do not understand. But since the Hubble telescope, we've actually been able to sort of map out what's been since the very beginning. Not the very beginning itself, but since, which is still pretty exceptionally different from what we had known even 150 years ago when we thought that this galaxy was all there was. So a breakdown would be just a reminder that it was not an explosion. It was rather an expansion of something so infinitely small. We only call it a singularity because we don't have a measurement for it, which began to stretch exponentially fast all at once. Again, we do not know what caused it, but it's important to remember that it wasn't filling in to anything except for itself. So there was nothing outside of the singularity at that point. It was all there was, but it just started to expand into itself. And so this expansion consisted of certain eras. Some of them are too complex for me to go into, but basically we started with inflation, which is what we are at right now, the quark era, the hadron and lepton epochs. I don't know how to say that. The opaque era, the introduction of stars and galaxies, and the universe that we know today. So the quark era and the natural laws. So quarks were formed from gluons, and we're under a second right now, and temperatures were so high that matter and energy were almost the same thing. And somewhere in here too, somehow, we do not know why, matter won over antimatter, and that's very important for us because that's one of the reasons why we're here today. So now at 1 second, the sort of undefined force is sort of getting more complex. Just 1 second in, we have a strong nuclear force, electromagnetic force, weak nuclear force, and gravity. God bless gravity. Even in 1 second, though, the universe has now stretched to 1 billion kilometers, which is ridiculously enormous in a change in size. Like, I can't even comprehend it, which I guess is the point. So the hadron and lepton epochs. So at this point in time, quarks began forming protons and neutrons, which are hadrons, and only some of these combinations were able to remain stable for relatively long periods of time. And after these hadrons and antihadrons, because everything has to have an opposite, the leptons were able to form, and these are electrons. And around this time too, energy is freed in the form of photons, which really means nothing until the universe is less dense, which it is definitely not right now. It's very hot, very, 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 very dense. So, in the nucleosynthesis era. So at this point in time, we've reached 3 minutes, and the universe is now 100 billion kilometers, which is, again, infinitely larger. So we've also dropped in temperature enough to allow neutrons to become protons through nuclear fusion. And this nuclear fusion also creates the nuclei of some of the simplest elements, being hydrogen, helium, and lithium. And 25% during this time of hydrogen was converted to helium. The other 75-ish% is hydrogen still. And after 20 minutes too, nuclear fusion is no longer the leading force in the universe, as the temperatures just drop too much. So in the opaque era, it's dark. It's the dark age, hence the term opaque, because it's just so dense right now that photons, when they emit their wavelengths, or their little zigzags of light, just other lengths, it's so dense and and there's just so much junk in the way that it just keeps hitting into likely charged particles, and no light is able to escape. And in the opaque air too, atoms are able to be formed out of hadrons, which have the protons and neutrons and electrons. So the first stars, it's after 180 million years before gravity can finally bring these clouds of hydrogen and form them into stars. So where they sort of condense in on themselves. So again, not that long ago, still basically 13.7 million years minus 180 million years. Still 13.7 years, million years, but billion years, but again, it's all relative. Oh, sorry, I lost my voice a while back and it's just barely coming back. So dark matter provided a gravitational scaffold for the first galaxies and stars. We don't really understand it, but without it, we would not have our galaxy even. So light was released from stars. The light released from stars allowed reionization to occur, and after 400 million years from the Big Bang, galaxies are finally able to form. So you might be wondering what the evidence here is to support this theory. And it would be firstly what we were discussing earlier of Hubble discovering the expanding galaxies, him discovering that they were basically getting further away from us, meaning that they were redshifting, and this sort of goes in part with the fact that the universe is constantly changing. Like the sky we see tonight is different from the sky we would see tomorrow night, next week, or a month from now. And the size of the universe too affects density, which thus affects the powerhouse ruling. So at the very beginning of the universe, there was a different powerhouse, like there was a different force running the universe. So it's sort of like a what's there to say there could be another force that we really don't understand that caused the Big Bang to happen. Right now, it's dark energy that's sort of running the show. But as you could learn earlier, that nuclear fusion had its 17 minutes of time to shine. And there's also cosmic background radiation, which is another important factor. And I even gave it its own slide because it's just that important. So basically, what we see today is what was emitted 13.7 billion years ago. But instead of it being the complex short forms of whatever it was before, it's been redshifted into radio waves along the electromagnetic spectrum, which explains why we can sort of hear it around the universe today, because it was coming from every point, and at that specific point in time, the universe was. It's really hard to explain. It's kind of confusing. So basically, this radiation appeared after 380,000 years, which is still 13.7 billion years ago, not right when it began, but when photons finally had the space in the universe to travel and emit their wavelengths. And basically, they were emitting these radiation wavelengths from every point in the universe. And today is what was emitted what we see today is what was emitted 13.7 billion light years ago. But it's just, we see it in radio wavelengths because it's been redshifted from what it was initially as emitted from photons, which sort of proves that it's expanding because it's different from what it was 13.7 billion years ago. So we can see it from every point in time, which you probably understand because you're a science teacher. But so the universe today, definitely 8.5 to 9 billion years ago is not really what we see today, but I thought it's important to mention that that's when our solar system was formed. Way around here. And so right now, dark energy is the powerhouse of the universe, and due to these unknown forces, aka dark energy, the expansion of the universe is no longer what we thought to be linear, but rather accelerating. And that's all on the Big Bang Theory, and I'm pretty sure I'm about to run out of time too, so very convenient. This is my bibliography, and I hope you enjoyed my little spiel on it all.